Thank you so much for the kind introduction. And yeah, actually, it's kind of a privilege for me to attend this wonderful workshop. As you see, I didn't find a longer title, so I put this one up. But as you can also see, and it's also a privilege for me, so I can take you on a journey because, as you see here, lots of the building blocks have, in a sense, already been presented this morning, so I can just try to weave it together. And yeah, just a little bit of background why I'm so excited about this workshop and also the topic to present is we as a company, in a sense, we have kind of like a great interest in AI on graphs, learning on graphs, deep learning, and now the more emerging field of topological deep learning combinations. Given that we work a lot on knowledge graph and their integration with language models and temporal knowledge graphs as memory representations, and also in various projects with respect to analyzing graphs and logistics and power grid networks for analysis and prediction. And me personally, in particular from my academic background, I spent quite some time working on random fields and also in genomics and epigenomics and analyzing gene networks in particular. And so what I would love to take you on a journey a little bit with me is basically one thing, in a sense, a little research topic in our company that grew out of last year's ICML Topological Deep Learning Challenge. And you can see here the small team that we formed and kind of like the mini task force. You see my talented colleagues Lil and Max and Dominic and actually me, and this is actually going to represent that I was at the time I saw about the challenge on vacation in Italy, so it's actually very authentic, me sitting with my coffee and noticing, and we were instantly excited, and I got in touch with my colleagues and we kind of like thought about, okay, can we contribute, can we actually do this, because also the challenge had this really nice feature of like having an open source contribution, this TopoBench library, where basically the idea is to bring together the research on topological deep learning and form a foundation for being able to really quickly test and evaluate. And given the limit in time that you typically have, was for us a super cool initiative and we wanted to contribute. So in that sense, we basically did, and the cool part was there was this design challenge basically, right? So it wasn't a really performance challenge, but the idea was to come up with liftings on various domains like graph-to-hypergraph, graph-to-complexes, and then basically there was this nice evaluation among the community, and we didn't expect, but turned out kind of nice for us, so we won in one of the categories, like second place, and so in a sense, I would love to basically share the design ideas and what we did in a sense too, and something that developed out of this a little bit. So the challenge we wanted to address with our lifting was that phenomenon of over-squashing that we already heard of today. And we basically looked into message pathing graph neural networks in a sense. And as you might know, like for the graph neural networks, in a sense in general, in particular for the message passing graph neural networks, the inferred graph has this dual role, right? It encodes the relationships among nodes, but it also serves them as the backbone for feature propagation. And to that extent, it kind of like tends to open the door for that phenomenon, information over-squashing, which is basically the loss of information due to compression over long distances, in a sense, or over exponential receptive fields, given the fixed size, in particular because of the fixed size representation of individual nodes. So when does it actually happen? So if nodes communicate along long distances, or as we'll see in a second in an example, if we want to pass too much information from too many nodes through individual nodes, that kind of like function as sort of a bottleneck. Yeah, and how does that occur? If we quickly remind ourselves of the sort of like the update rule for these message passing neural networks, basically what we have, given one particular node vi here, for example, we update its representation by aggregating the information from the neighboring nodes, and then performing kind of like a node update. We have a few more nonlinear layers, functions in between, but that's kind of like the general procedure. And now if we basically kind of like unfold the network operation along the network's layers, then in a sense in time, then what we can see and what we can visualize is that information propagation along the network graph itself. And as you can see here, for example, if I reach layer 3, I got information from these exterior nodes at the top, all basically having information propagated down and for example, here that V beta would then, in a sense, form that sort of a bottleneck, right? So we have a fixed node representation there, and we're trying to squeeze more and more information through it. And at some point, xi, a lot of information is basically going to be lost before it reaches xi. And just as a side note, in a sense, kind of like another reason for that information loss in these message passing graph neural networks can also be if the distance between the nodes where you want to exchange information from is higher than the number of layers. So for example, here in this xi to xj, in a sense, in that simplified example, we would have a distance of 4, whereas we already stopped at layer 3 in propagating, and then in a sense never really reached the final node. So as already has already been really nicely been illustrated this morning, we looked into metrics in a sense to identify those bottlenecks and try to see how we could use that. And in a sense, the literature suggests to basically get a better understanding of the oversquashing phenomena and its relationship to the graph by using geometric properties, in particular curvature, as I mentioned, as we've already seen this morning. And I can really recommend that nice paper by Topping et al., who really nicely visualized that. And so that's something we looked into. And as we've heard, what we can nicely do is, in a sense, create these analogies between continuous curvature on continuous manifolds, and then basically having these analogous mappings to the discrete domain. And then there's also a number of interesting curvature measures on graphs, in particular the Olivier-Ricci curvature. Basically, it intuitively translates this notion of the Gaussian curvature to the discrete domain, but there's also others. And so that's something we kind of like looked into. And in a sense, due to being on vacation and hence lacking experimentation time and computation resources at hand, I kind of decided to go with a very simple and fast method, also been introduced this morning, and that was like the original purely edge-based Forman-Ricci curvature, in a sense. And the theoretical motivation for this was like, okay, saw that both sort of like are described to, in a sense, in part share some of the properties that they measure, but one being obviously faster than the other one. We had to sacrifice that nice intuitive notion of just being able to kind of like translate Gaussian curvature as is, positive, negative, and neutral, to the discrete domain, but I was willing to do that in a sense. And so the additional cool part with this sort of a little bit more elaborate original equation on the left, which takes into account like node and edge weights and everything, is that for as we've seen this morning, if you basically apply to an unweighted graph, the whole thing really nicely boils down to this handy equation that kind of like depends on the degrees of neighboring vertices around an edge that we want to evaluate. Right, and so in a sense we use that, as you mentioned. Actually, maybe your notion wasn't that far apart. Indeed, we kind of like used this notion of curvature as kind of a microscope in the graph in order to identify and to mark or label bottlenecks, in a sense, for the lifting later. What has been suggested in the literature, again, going back to this really wonderful paper, was to apply some sort of like local graph rewiring. So what that basically, as you can see here, means is that we sort of smooth these like bottleneck connections by adding additional edges and potentially additional nodes in order for information flow to basically happen. What we thought is like the limitation being, the limitation being that still we're working with pairwise relationships, so that doesn't necessarily solve the problem of long distances. And in addition, we kind of like potentially increase the graph complexity as we're adding more nodes, potentially adding more edges. So in a sense, what we kind of like decided to do, also obviously in line with the idea of the challenge, was to say, okay, let's use curvature in a sense as a guide to then create some graph-to-hypergraph structural lifting, so lifting of the network, which would also potentially make the network, in a sense, for the subsequent classifier a bit easier instead of more complex. And that's, in a sense, what you see here in one slide. That's kind of like what we then sort of proposed and implemented, was to first exploit the curvature measure. And here we used, as I mentioned, the Forman-Ricci curvature as a metric to label the graph edges. And you see that here as an example for a very simple unweighted toy graph. And after we've done this, we basically created the structure lifting by defining the hyperedges in this mapping from G, the original graph, to H, the hypergraph, kind of like in this framework being represented as a bipartite graph between vertices and hyperedges. And what we kind of like required, so in this initial version, what we worked with was a single parameter in a sense that would act on the distribution of Ricci curvature edge values. And then we basically would form two groups. One of the groups being an hyperedge being defined as all vertices that are adjacent and also have a Ricci curvature above the threshold and the other one going below. Yeah, for the construction of the final graph, we didn't really distinguish then whether it was above or below, but this was just to kind of like create it. And then, so what I mean is the individual hyperedges didn't get like a different weight or something, right? They would just, okay, want to see how many, and so in this particular case, we would create 5 hyperedges and then have the corresponding number of vertices being assigned to them so that we could create this nice bipartite representation. This is more or less already what I already told you in a sense, just here for formality a little bit, like the formal definition, but I already mentioned how we kind of like did it, so not really of interest. And then, as I mentioned, and this is something kind of like which needs a little bit more evaluation, is to say, okay, we lifted, in a sense, within the challenge set of data sets, we kind of like wanted to make some experiments. We took sort of like common graph neural networks in particular. Here we were interested in the message passing graph neural networks, and we lifted the original graph data sets to that bipartite hypergraph representation. And then, in a sense, and that's what you can see in the table on the bottom right, we checked if we can recover or even go beyond, in a sense, the original prediction results. And for stability, in a sense, what we did is we kind of like averaged the results across different metrics per each data set and model. Yeah? And as you see with the asterisks, so one of the things that we basically have currently on our to-do list is to go a little bit more into the evaluation of more long-range data sets, right? Because these here are kind of like standard data sets that we took from the challenge, but that's something obviously that we were all really interested in, and therefore that's sort of like on the menu. Yeah, and with that, I thank you for your attention.